Good morning. Welcome to our latest webinar, Solving Manufacturing Problems with Sensor Feedback. I'm one of your hosts, Ed Stockline. I am one of the sales managers here at Promess Incorporated. I've been with Promess for about 10 years now, worked through applications engineering and final assembly, now working with the sales team.
Hi, I'm Gibson Kramer. I'm an application engineer here with Promess. I've been here for about 1 year, and we're going to be going into some pressing here with our press and some program examples.
So some housekeeping things initially for you guys. If you do have any questions during the presentation, off to the side, there's a questions box where we'll get to those questions towards the end of the presentation today. We may get into some questions that may have a little bit more depth than we're going to cover in this webinar. If we do run into any of those questions, we'll reach out to you or shoot us an email, promess@promessinc.com, and we can handle those deeper questions. Another part of the webinar today, we're going to have a split screen where there's going to be software and the camera of the press RAM. You should be able to move your window to show either more of the camera or more of the software, depending on what we're talking about. So that's something that you can do on your computer as you're going through the webinar with us. So today we're working with a benchtop workstation here in our process development center. This is a standard size workstation from Promess, what we call our benchtop. This particular model has a 3 kilonewton, 300 millimeter stroke EMAP on it, which stands for electromechanical assembly press. The press itself has an encoder built into the motor, which gives us our positional feedback. And the silver band at the top is actually the strain gauge load cell, which we can pull the force data from the process into that sensor and bring that into our software. So we're going to have Gibson walk through some of the basics of the UltraPro programming today, and then we'll kind of cover a couple applications that each of those basics can apply to, and how we can use different feedback to solve those problems. So what are we going to look at first, Gibson?
All right. First, going into the software here, when we first open this up, we will see the basic screen. All right, and this is what that looks like here. Here we have a title for the program, a couple live readings, and as we build our program and add monitoring and gauging, you'll see these blank areas fill up with your data. All right, we're going to move into the editor tab. Here I have prepared a very simple program. This program will be moving down to the part, which is the first move step here. The second move step will be actually applying force to the part, and then the third one will be a retract. As you see, all my move steps here are all in the positioning column. In the main column, we will be adding different gauging steps, working with program flow, and evaluating the data that we grab. All right, so I'm going to start by just running this program here. If you watch the press camera, see it comes down, presses on the part, and retracts. As you notice here, I didn't retract all the way up to home. I'm able to just move back to 150 here, which is in millimeters, and that will give me enough space to go in, move components and everything like that. This is a very simple program, and we currently don't have any way to pass or fail a part. So the first thing we're going to do here is add a monitor. I'm going to go over to the monitoring tab, select a new monitor, and the most used monitor type we have is a force and position. All right, here we see my name popped up. This is the monitor, and these are the different settings I have for that. You can see on my x-axis I have position, which is in millimeters, and my y-axis I have force, which is in newtons. All right, with a super basic monitor setup here, we'll go back to our steps. And in the program here, we will tell it when to start acquiring that data and when to stop. So I don't want to acquire data for my positioning, my first move here, down to the part. So right after that, I will add a monitor trigger. Here I am starting it, so it'll start acquiring data once the program moves on to this step. And then after I press down on my component, I will add another trigger, and this will stop and analyze. All right, so I will save to controller, go back to my HMI, and now you can see I have a little graph here. I will go ahead and run a cycle. And there we go. Now we have our force versus position graph. All right, and now we'll start pulling a little bit of data off of this. So the first thing I want to look for is a peak force and a final position. All right, so I'll go back to my monitoring. With my monitor selected, I'll go to my toolbox and I'll add a maximum X. I'll change this. This will be my final position. All right, save to controller. Then I'll go back to my steps and add a gauging step in the main column. In these gauging steps, we're able to take data from our monitor and give it a set of criteria that will either indicate a pass or a failure. So my label here, I will do final position first. All right. And this will be a function result, final position, and I want my X value. And you'll see in a second here, I also have the ability to grab the Y value there. All right. And to set my limits, I'm going to go back, take a look at my first monitor here. Looks like I'm between about 251.5 and 252.5. So I'll go ahead and add those here. 0.5. All right. And then with the gauging step, I will be enabling storage. And this will save the value that I gauge to a separate spreadsheet here that we'll see in a moment. I'm also going to add a gauging step that will be for my peak force. All right, and I go back to the same function result, but this time I want to select my Y value. And when I do that, the system knows that my Y value for this monitor is in newtons, so it automatically sets the units there. Once again, I'll go back here, take a quick look. I'm going to be between about 800 and 1200 newtons. So my lower, 800 and 1200. It's pretty typical when we're first setting up a program to kind of leave these open. And then once we run more and more cycles and we evaluate to really determine what's a good part and a bad part, then these limits can be tightened up. All right, I'll save to controller. Make sure I enable storage. Save once again there. And I'll go ahead and run a cycle. Now you can see a little indicator right up here. This is showing me where we're grabbing that data from. So we have our final position, which gives us our peak force and our final position. All right. So far we've been using a move to position step. And this type of program can be useful in situations where you don't want to drive the part all the way down to a shoulder or a hard stop. And this can be a pin or like a dowel pin for alignment. This can be staking or crimping. There's many different applications where you would want to just use a move rather than a move to signal. But that's what we're going to move towards next here.
Yeah, so the at least with the press position, you know, Gibson mentioned pressing a dowel pin. So that would be where you have tooling on the press ram that you're pressing the dowel in to, say, a required install height. Say you're mating two cast aluminum housing pieces together. You need those dowels to stick out a certain amount. Staking, so typically in staking, the stake depth is the most accurate way to determine whether or not you have a good stake. And a positioning movement in most instances is a really good way to accomplish that, because we can be really repeatable on that positioning and make sure that we're hitting that stake depth each time. The other ones that you had mentioned, anywhere where say the material kind of changes and it might have different force values required to, say, crimp something over, assuage something over, but the positioning is really critical in those applications. Swaging, for example, if you're pressing tooling into, say, a copper tube to resize the ID, it's really critical that you only have maybe an inch of travel inside of that swage versus just pressing to a force, because you may never actually achieve a certain force if you have, say, a thinner wall material or something that isn't conforming. So yeah, go ahead and start with the next one you mentioned was the move to signal. What's a move to signal?
Yes, Ed. So a move to signal step. Here, I'll add one for us. A move to signal step is a closed loop step that will continue moving until it finds your target force. So on this step, in these settings here, I can see my control input is force right now, which is taking that force from the integrated load cell. That can also be different integrated sensors that you can select here to move till we find an input based on that sensor. My target value here, I'm going to do about 1200. And my speed, this is typically about 2 to 10 millimeters per second. I'll go with 5 for this example. The reason it's a little bit lower value, especially if we take a look at our move step here, we're moving at about 125 millimeters per second. With the move to signal, we want that to be a lower value, which will increase your accuracy and your ability to stop at the required target value.
You don't want to overshoot, right? If your speed is set too high, the press might not have time to react to that force feedback, especially if you're running into a hard stop or a shoulder.
Yep, exactly. Same goes for the acceleration and deceleration. These are typically going to be the highest value for your system. In this case, that will be 1,000 millimeters per second squared. And especially with the deceleration, having a high value here helps the system react quickly to the time when we get that target value. For example, if this was lower, it would take more time to stop after that target value was reached. So to reduce overshoot, we set the deceleration to the maximum. Another thing we'll go over here is the maximum travel. So in a situation where I don't find my peak force, which here is 1200, if I don't find my peak force, this system within this step will keep going until I reach 300 millimeters, which is the maximum travel for this system. It's useful adjusting this maximum travel value to a position where the part isn't present. So you can use this to do dry cycles. If you get to this force, if you get to this position without getting to this force, the system will stop. And similarly with minimum travel, this will allow you to set a threshold to where you want the press to go at least down to this position, even if it does reach the target force. All right. Here we go. I'll go ahead and remove my old positioning move here. Here you can see I have two options. I can delete just a single step, or I can delete the whole row. All right, and ready to save to controller. Go back to my HMI. All right, there you see, we actually failed that cycle because of my previous gauging step limit. I'll go ahead and adjust the peak force here. All right, so now let's say we want to make sure that this will fail a different part. So I'm going to go ahead and swap out the springs here. I have two different springs with different spring rates. Let's quickly swap these out. All right, and in this situation, since we're moving to a target force and we're bottoming out, even though the spring is totally different, this cycle is still going to pass. So what we're going to want to do here is add additional monitoring in the actual press area that will allow us to fail this orange spring. All right, so I'm going to go ahead and quickly switch back. And I'm going to go back into my monitoring. So here, when I'm in my monitoring tab, I'm going to press show graph and select a reference curve. So the last one we ran, we want to be able to fail that curve. So I'm going to use this previous one for my reference. Go ahead and set my curve. And here we're able to visualize in real time as we add additional monitoring to our graph here, okay? So I'm going to start with a window. This window is going to go from about 238 to 248. All right, and there you can see, shows up right away. And then within this window, while I have the window selected, I'm going to add relative limits. So I'm going to do a relative upper. And going back to the window, I'll do a relative lower. All right. And now, save to controller. We'll run it once with the white spring, make sure it passes, and then we'll run one with the orange spring to show a failure. There you go, we're pretty close. We'll go ahead and swap it out. All right, and here you can see, even though my gauging passed, I was still able to fail the cycle because I'm outside of these relative upper and lower limits.
And so essentially what Gibson's done here is he's taught the system what a good part is. And the really powerful part of these relative limits, or really any of the strategies that you build around your parts profile, it's going to allow you to capture the anomalies. So if you're running a high volume operation, you're not going to have your operator babysitting and visually inspecting every single part that comes off of a station, or at least you don't want to in most cases. But this will really allow you to lock down what a good part is determined by your engineering group, and then be able to compare those to every single part that comes off your production line. So where would we use a press to force program in the real world, Gibson?
Well, the most typical applications for this would be a bushing or a bearing where we're bottoming out the part into the mating surfaces. This can be really powerful to make sure that we actually bottom out the part every time. If we're moving to a position, there may be some tolerance stack up or other conditions which make it so we don't bottom out, but here we're ensuring that we're going down and pressing the part in every single time.
Yeah, so if you have a pretty tight tolerance on an ID and a pretty large tolerance on the OD of a part that you're pressing in, you could actually spike up and hit your target force fairly early in the process too, right?
Mm-hmm.
And you would probably fail the part with your monitoring strategy as well.
Right. That's always the goal, is to have our monitoring strategy being able to determine whether it's a good part or a bad part.
Another application that is fairly common, especially in this day and age with electric vehicles, pressing and seating rotor and stator cores in electric motors. So having a program that can continually stack all the components in a rotor or stator and change with your position changing every single time, you actually are just looking for that force to make sure something's fully seated versus expecting or running the press to a final position.
Yes, especially with the differences in positions, whether you have some parts that are max material condition or least material condition, a move to signal will make sure that we're going to the same force every time.
So what about some combinations of force and position programs? Do we do a lot of those?
Yeah, we actually do quite a bit where we combine both the position and the move to signal step. I can go ahead and demonstrate a program here where we will actually use the move to signal step to touch off on the part, and then from there we can do a positioning step, which is relative to where we found our force.
So why would that be useful?
If the component isn't in the same location every time, we're able to come down, find where that part actually is, and then we can move based on the position we find that part at.
Yeah. So like if an operator loads a part and it might be slightly misaligned or a little bit higher on one side, we can actually kind of align with that initial force and then begin our critical press move at that point too.
Yep, exactly. All right, to find my touch point, I will use, again, like I said, move to signal, but I'm going to reduce the target value to about 30 newtons, which is a relatively small load for what we're doing here with these springs. And then from there, I will do a move step, but this time I will do it relative. So with that spring in there, I'll move a relative 10 millimeters. Again, I want this to be a relatively low speed. Make sure I add my overload limit. All right, and now, so the press is going to wrap it down to 235. It's going to move until it finds the part with a small force, and then it's going to move 10 millimeters past that point. All right, save to controller. And there we go. That can be very beneficial when you're looking to move based on where the part is in space rather than where it's kind of supposed to be. So.
And we actually, on that HMI, we failed the part, obviously, because we didn't get to the full depth, because we didn't press the additional, say, 20 millimeters or so that's required to bottom out this particular tooling. We also failed the final position and peak force, but we also failed the limits too.
Yep. And as you go and develop your process, you will want to be making small adjustments to the gauging in your monitor to really nail down what a good part looks like versus a bad part. And these monitoring strategies are really helpful for eliminating different failure modes. So if you have one failure mode that is the part being too loose, then this bottom lower limit will make sure that if the force is too low during the pressing operation, then it will fail that part. And if the part is too stiff, it'll cross the upper limit and fail the part for that reasoning as well.
So for those of you that haven't experienced data collection like this in your assembly process, we do have our process development center, which is where we're currently located, which we have workstations similar to what we're using today that are ready to go. So if you're unsure as to what the signature, the fingerprint of your part looks like, you could actually send us parts and we can work with you to develop the process and make sure that before you even spend a dime on capital equipment or assembly equipment, that the equipment's capable of what you need it to do. Maybe you're doing something a little bit odd that hydraulics or pneumatics can't actually perform certain movements. You can develop that process here in our lab and ensure that you're going to get the right equipment selected for you. With that, I think we have some questions. Let's see. So Gibson, how accurate is that press position?
So the press position is accurate to about 25 microns and repeatable down to 4 or 5, which gives you very repeatable results when you're pressing the system. And if you do see a variance within that that window there, then you know that it's a variance within your parts and not just a variance with the pressing equipment.
So what's the difference between the accuracy and the repeatability on that?
Yeah, so the accuracy will be essentially, if we say we're at 150 millimeters, then there's a plus or minus 25 microns on that value.
Now, that's the absolute value of the press, right?
Yes, the absolute position of the press. The repeatability, if we were to run this cycle 50 times, then we would see a repeatability within 4 or 5 microns.
So once you program that position, it stays within that 4 to 5 microns.
Exactly. Yep.
Okay. And I believe that's under constant temp and constant load in a production setting. The next question, can the system tell when we've bottomed out?
Yes, actually, that is one of our advanced monitoring strategies. We can program the system to recognize rate of change, where it will stop the press once we see that large spike in the force. If you're interested in applying that type of process to your application, reach out to us and we'd love to help you out with that. It can be very helpful. Make sure you're bottoming out the component, but not stressing all your tooling and fixturing more than you need to.
Yeah, we see that a lot with electronics. We don't want to overpress and potentially break circuit boards, right? In a lot of the scenarios. So it's usually when you're pressing a couple delicate parts together or parts that have a certain profile that has to be, a lot of attention has to be paid closely to.
Yep. Can be a very helpful tool.
Let's see. How many monitoring windows can you have in a single program?
Well, here with, if I go to my monitoring and I show list, I am able to add a very significant amount of monitors here. Just add a couple more here, and then we can see them pop up over here once we save to controller. Back to the HMI, you can see I can have a very large amount of different monitors across my top window here.
And then inside of each monitoring strategy, you can have multiple windows where you're looking for different different properties of that data, right? So like a snap ring, for instance, you're gonna start pressing, see a climb in the force, and then a drop down in the force once the snap ring's popped into the groove that it was designed to go into. You can monitor the snap force in that, and then as you fully seat the snap ring and press it to a final force, you can also capture the peak force and final position where that snap ring was placed.
Yes, exactly. So if you have a application where you're pressing in multiple components along the stroke, then you can set up separate windows to monitor those separate component engagements.
Okay. Another question here. Is there a way to pass data out to a server or tie a barcode as a variable into the system?
Yeah, so we'll start with the serial number here. You can see I have a serial number that shows up in my gauging, and this will be for each component. And we can actually accept string variables through the PLC, where we can assign that string to a specific cycle number, so you can correspond your serial number with the data that it was used to press with. So.
And if you don't have a PLC, say you're in a lab type setting, you can actually add a serial number manually. And if you have a barcode scanner that's a USB barcode scanner, you can plug that into your PC, and it will actually input the serial number for you, or whatever you scan. It could just be a batch number or something like that, depending on what you're doing.
Yep.
And then the second part of that question is there a way to pass data out to a server?
So we do offer what we call our data service, and that will be able to go into the controller and grab the data and then save it to a location, whether it's on the server or another PC.
Yeah, and the data service is an added piece of software that goes with our systems, and that's usually stored on like you mentioned, a remote server, right?
Yep.
Okay, is that it for questions? Looks like it. Okay. Well, we certainly do want to thank everyone for joining us today. If you do have any questions about our Ultra Pro system and the programming, if you would like to see a demo, please reach out to us. Gibson mentioned our rate of change programming and some more advanced programming techniques and monitoring strategies. We'd be happy to set up a demo and show you some of those if your part requires it. If you want, you can reach out to us. Our phone number here at Promess is 810-229-9334, or you can reach out to Promess at promessinc.com or sales at promessinc.com. Excuse me. Thanks for joining us, and have a great day.